Vector equation of a line. Suppose a line passes through point A and has direction given by D. We can see that in the diagram. So A is a fixed point that we know is on the line, and D is the direction in which the line is going. R is any point on the line. So R is a movable point, and it could be at any position along the line, even going backwards from A. Now, OR, so that's going from the origin to R, so we're talking about this vector, using vector addition, is equal to OA plus AR. In other words, going along here and then along here. And that means that we can write that as R, that's the position vector of R, is equal to A, which is the position vector of the point A, plus some scalar multiple lambda times D, which is the direction of the line, for some scalar lambda. So if we have the situation where lambda is equal to 0, then R is just equal to A, and so we are at the fixed point that we know. And then as lambda changes, we move along the line. So we have lambda is 1, lambda is 2, lambda is 3, lambda is -1, and lambda is a half would be the midpoint between where lambda is 0 and lambda is 1. We saw this in the introduction where we had R was 215, that was the fixed point on the line, plus T times 3 -4. So 215 was the A, the fixed point on the line, and 3 -4 was the direction of the line. Every hour it went 3 units east and 4 units south. The vector equation of a line passing through the fixed point with position vector A and parallel to the vector D is given by R equals A plus lambda D. R is the position vector of the body at time t, that's at any time. A is the position vector of a fixed point that we know is on the line, and D is the direction of the line. Lambda is just a scalar variable, so that as we move along the line, we have lambda, this is y, lambda equals 0, lambda equals 1, lambda equals 2, lambda is -1, would be back this way, I've written y again, lambda equals -1, and lambda equals a half would be the midpoint of where lambda is 0 and lambda is 1.